All right, we're going to talk about just going back and forth between coordinate points that are in polar and rectangular. So you can do it either way, but sometimes there's advantages to converting it to one or the other. With polar, if you have an r equals 3 and a theta is pi over 3, there's a conversion we've been using. R cosine of theta and R sine of theta are where we get our x and y. It came from our history of using vectors. We just know that magnitude cosine of theta gives you the x component, magnitude sine gave us a y, and then r is the radius in polar, which signifies that same hypotenuse that the magnitude did when we were graphing in vectors. So it's the same conversion formula. So if you have r and theta, you just do r cosine theta for x, r sine of theta for y, and I've got my xy polar equivalent right below a there. 3/2, 3 square root of 3 over 2 is the same as facing pi over 3 and going out 3 units, exactly, plus the exact same point. Same thing on the next one, r cosine of theta, r sine of theta for x and y respectively. These are on the unit circle, so you can do them exactly with radicals. So you want to have a unit circle handy when you make that conversion. Okay. And then the other way, if I have the point 3,5, then what we need is an r, and that you'll get from that distance formula, x squared plus y squared, and then square root it to get that length, that hypotenuse length, if you triangulate the over 3 up 5. That's your square root of 3 over 4, that's your radius. And then theta is the inverse tangent of y over x, and then you have to cognizantly decide, is that the correct angle or do we need to add 180 to it? This one is 59.05. That makes sense with the point I plotted, and so therefore I'm going to use it. So my polar point is the square root of 34 comma 59.05, radius comma theta, seemingly backwards, of course. B, same idea, x squared plus y squared square rooted will give you that r, so square root of 17 in this case. And then the inverse tangent is going to, of x over y, is going to give you an angle, so I get negative 14.04, but if you look at my plot of the point B over to the left, yeah, that's facing the wrong way, it's 180 off. And so you might jot that down and go, whoops, 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 whoops. I need to add 180 to that because it's facing the wrong direction. And then that's it, that's your correction, and you can get a value for that. Okay, so last one. So any coterminal works, technically, when you're doing these are direction angles. But usually we just use the positive angle that's most convenient to you. But any coterminal would work. Remember, there's an infinite number of ways to write a polar coordinate because you can face an angle in so many ways. Okay, and then there's this last one. There's an r and a theta, same technique. You want to make sure that you're just very careful that that angle that you get, negative 45, is the inverse tangent result. I know it from the unit circle, but I also just, maybe you typed it in your calculator, but look at your point to make sure it's facing the right way. This one is, you could use a positive angle if you prefer, but I'm going to stick with that negative 45 and call it good. Okay. Next piece. So when I do this r cosine of theta, r sine of theta, it is because if I plot a point with xy coordinate points, there's a theta and an r that get you to the same place, and it's all part of the same right triangle. And in that right triangle, you can write some really nice equivalence statements, like cosine of theta is x over r, and sine of theta is y over r, tangent of theta y over x, r squared equals x squared plus y squared. Those are all things about that right triangle that I'm sure you can see are very true. And you can manipulate those all you want into different forms, but that's where that stuff's coming from. These are just ways of describing the same scenario. This is just a couple more examples. I thought I just finished this off. I went ahead and we'll do these kind of quickly. If you have an r and a theta, you can find x and y by simply doing r cosine of theta, r sine of theta. Be exact with the unit circle and leave your radicals, and all will be well. Okay, so I'll let these just kind of play through quickly. You can check them on your own time and see where they come from. Just get a unit circle, have it handy when we get to the test, and you'll be in good shape. And here's the last one. With 116 degrees, that one is not on the unit circle, so you're going to get those values, and then you're going to plug them in there. But one thing you want to check out is make sure it's okay. If I face 116 and I plot 3 units out with my 116, just make sure that the x and y, negative 1.34 and 2.7, makes sense and land you there, and it does in this case. But you always want to double check that everything is sensical. Okay. Now at the bottom there's this radar business, and I wanted to plot these 2 points and just give you an idea of how this works. But what's cool about this is that you're going to plot 2 points, and if you face 110 and walk out 8, or face 15 and walk out 5 units, that's a sense of that's how polar works. Usually, though, in the functioning world, they use bearing, but we're going to go with direction angles for right now to keep the calculations relatively simple. But if you want to know how far apart they are, you could graph it on some really nice graph paper and measure it, of course, with a ruler. That'd be just fine if you had some really nice polar paper maybe that you graphed this on. However, we could also just plot the points and use the old-fashioned like distance formula, but that's conducive to having the xy coordinate points. So we're given polar, we plot the points, but I'm going to convert it to x and y because I have a way of getting distance between 2 points in the old xy coordinate system. So I could find that length. If you remember, we made a right triangle out of it, and we just find the x squared and y squared distances there and square root them to get the length of that hypotenuse. So we'd find, the distance between y's, subtract them, distance between x's by subtracting them, and then ultimately we're going to find that length d, the distance up top there, in its Pythagorean theorem, right? X squared plus the y distance squared plus the x distance squared we get from subtracting. If you square root it, you're going to get that length d. That's the old distance formula. And when we plug it into ours, you could also, if you wanted to find d and you had those sides, you could actually use SOHCAHTOA, since that is a right triangle, if you happen to know some angle inside there. But I don't think you could try and get that angle inside there, but I think that's more work than necessary. So my recommendation, go with that distance formula. Take your polar, whatever coordinates you've got, and let's make the xy coordinate equivalents. So the first one, 1/10 and a radius of 8 miles. We're going to make 8 cosine 110, 8 sine 110, and similarly we're going to use the 5 cosine 15 sine 15 to make the x and y for the second point. Here they are with my calculator, decimals and all. And then to get the distance between them, we subtract the x's, and in no particular order because we're going to square it, so negative or not, it won't matter. But I'm going to do the right minus the left, and then again subtract your y's, right minus left. The order is not going to matter since we're squaring it, but I like to be consistent if possible. Add the distances squared, and then square root the whole thing, and we get the d distance, our hypotenuse, of about 9.8 miles between those two. So that's an application of, hey, I got polar. Would it be nice to convert? What would I want to convert to x and y for? This is, one way that might come in handy. Okay, I'm going to go on to the next section.